I'm Ciamac Moallemi. I will be giving the second part of our tutorial today on automated market makers and loss versus rebalancing. And what we're going to do in the second part is we're going to build some mathematical formalism around the ideas that Jason described in the first part. We're also going to introduce some ideas from convex analysis to look at automated market makers and related mathematical objects. And that'll tee up for the third part where Tim will circle back and develop some of the mathematical theory for loss versus rebalancing, in particular incorporating ideas from continuous time finance. So with that, let's go ahead and get started. So we're going to talk about automated market makers. Sometimes they're also called constant function market makers. We're going to see where that name comes from in just 1 second. But just to set things up, without loss of generality, we're going to imagine that we're dealing with two assets. So the first asset is going to be a risky asset. We're going to typically denote that by X. And so our running example will be Ethereum cryptocurrency. And we'll be looking at a mechanism which allows exchange or trade of the risky asset for a numeraire or cash asset, Y. We'll typically denote by Y. So there you can imagine US dollars or perhaps some kind of tokenized version of US dollars. This is without loss of generality in the sense that the theory applies if we have more than two assets, also applies if neither of the assets is a numeraire or so forth. But this is sort of the most basic framework to sort of start thinking about these ideas. So one key part of the definition of a particular instantiation of a constant function market maker is a bonding function. That is a function which we're going to denote by F for the balance of this talk. It is a function of the quantity of reserves of the two assets X and Y. And we're especially going to be interested in level sets of this function, F of XY. So again, on the graph, X is the quantity of reserves held by the pool of the risky asset. Y is the of the cash asset. So if you want sort of a mental model, a nice kind of running example, and maybe the earliest and most famous case is the case where F of XY is a product, or equivalently a geometric mean, right? So this is sometimes called the constant product market maker. And the idea is we're going to leverage the invariant set of this function F to define allowable sets of reserves for the pool. So we imagine we have a set of liquidity providers, and maybe at time 0, they contribute assets X0, Y0, and take the pool to some state where it satisfies the invariant F of X, Y equals L. So that's the way the pool starts. Now, whenever an incoming trader arrives, they're presented with a menu of options. In particular, they can move the pool reserves to any point along that invariant curve. In other words, any point where F of XY equals L. So for example, this point X1, Y1 is another point where F of XY equals L. And so that's an allowable trade. And what that means is if we have an agent who wants to move the pool from this state to this state, the smart contract of the pool permits it. And in order to do that, that agent must contribute a quantity of the risky asset X. We're moving to the right on the horizontal axis. In particular, they must contribute the quantity X1 minus X0. And in exchange, because we're moving down on the vertical axis, they're allowed to withdraw the quantity Y0 minus Y1. So if you just think about that for a second, that's a trade. That's a trade where you sold a certain quantity of the risky asset to the pool in exchange for redeeming a certain quantity of the cash asset. What was the price of that trade? It is simply the ratio of those two quantities, and it is given by the slope of the hypotenuse of that triangle. Right. So this is a mathematical formalism that defines what Jason promised. Jason promised that we're going to have a menu of options where you can come in and you can trade whatever quantity you want, and the price of that transaction will be determined by the level of reserves in the pool. And this is exactly that. And namely, the precise mechanism is maintaining the invariant of the bonding function f of x comma y equals L. Now, if we sort of think about maybe shrinking the trade size, rather than, of trading a finite quantity, trading an infinitesimal quantity, we reach the next object that Jason described, and that's the spot price. And so the idea is, if I'm at this point, the red point on the invariant curve, and I imagine doing an infinitesimal buy or sell, well, the exchange rate I'm going to get for the risky asset in terms of the numeraire is going to be given by the slope of the tangent to the invariant curve at that point, and that is what we call the spot price, the price for an infinitesimal buy or sell. So those are the core mechanics of trading. There's a couple of additional things, that are layered on top of that. The first is that fees are collected, right? So here, for example, I'm contributing the X asset, I'm removing the Y asset. The idea of a fee is that in addition to this state transition that's permitted, in order to effect the state transition, the agent must also contribute a fee that's proportional to the quantity traded, right? So, for example, in the Uniswap V2 smart contract protocol, the rule is that you're allowed any state transition on this curve. However, when you make a state transition, in addition, you have to contribute 30 basis points or 0.3% of an additional amount of the asset that you're contributing. And this is akin to the idea of a bid-ask spread in traditional financial markets. In the absence of a fee, as I sort of just described, the net price for a buy versus a sell of a very small size would be the same. And there's sort of deep reasons driven by adverse selections where you do not want that. You want to charge a different price for a buying versus a selling. And this is sort of what is accomplished in traditional markets by the idea of a bid-ask spread. And the fee allows us to have that structure also for automated market makers, right? So that's the second thing I wanted to discuss. And finally, the third thing is what happens with the liquidity providers. I mentioned at the beginning we were imagining a scenario where the liquidity providers, started at a particular state. However, the liquidity providers don't need to be static. Also, they can arrive and depart. You can have additional liquidity providers arrive and also contribute assets to the pool in proportion to what's already there. That's called minting. And when additional liquidity is provided, basically we move to a different level set. The value of L would increase, for example. Similarly, you might have existing liquidity providers who decide that they do no longer want to provide liquidity. They would withdraw their pro rata share of the asset in the pool, and that would correspond again to moving to a different level set, perhaps decreasing the value of L in that case. Right. So the overall structure is that for the arriving traders, they're forced to maintain the invariant. On top of maintaining the invariant, they pay a transaction fee, effectively equivalent to a bid-ask spread. And finally, from the perspective of the liquidity providers arriving and departing, that's moving from one level set to another level set of this curve. So that's the core structure. What we'd like to do is we'd like to do analysis of these objects. And in particular, we're going to employ some very useful tools from the theory of convex analysis. And our starting point for that is an object called the pool value function of V of P. And V of P is defined as the value of this optimization problem. The reason why V of P is important is it encodes sort of the relationship of arbitrage to the pool state. In particular, if we imagine one input to the function V is this object P, that is a price. And the idea here is, suppose that an agent arrives, we're going to call that agent an arbitrageur, and they really believe that the value of the risky asset in units of the cash asset is P. They really believe that that's the fundamental price. Perhaps they observe that price on other exchanges or what have you. What that agent will do is they will trade against the pool and they will try to make money if the price on the pool is not P. And by virtue of trying to make money, because trade between the agent and the pool is zero sum, the agent maximizing the amount of money they can make, again, when they believe the price is P, is equivalent to the pool's value being minimized. Right. And that's the structure of this optimization problem. We're optimizing over sets of reserves. We require the sets of reserves to be feasible in the sense that the invariant is satisfied. So we're going to restrict ourselves to be points on that line. And what we're going to do in the objective is we're going to seek to minimize the value of that point, assuming that the price of the risky asset X is P, and of course Y is the cash asset, so its price is always a 1. So this is an optimization problem. The key important fact here is this is a minimization, and that is because we are in an adversarial environment, right? We are trading with someone who is trying to extract value and hence is minimizing our value. So that is the idea of the pool value function. And we're going to make some technical assumptions for the third part of the talk. We're going to make the assumption that an optimal solution here exists. We're going to call that optimal solution X star of P and Y star of P. Those are the reserves that would be the optimal solution here. And the idea is whenever the price is P, we expect arbitrageurs to move us to the state X star of P, Y star of P by nature of being profit maximizing and therefore trying to minimize the value of the pool. So we're going to assume that a solution here exists. And we're going to assume some smoothness properties. And for all automated market makers that we are aware of, these properties are satisfied. So that is the pool value function object. Why is this important? Well, a couple of things. I've already mentioned that it mathematically encodes the arbitrage relationship between prices and pool reserves. However, it also gives us an alternative description of the state of the pool. Later on in the third part of the talk, we're going to reason about how this pool behaves dynamically over time and try to understand how much money the liquidity providers make or lose. And as we track the state of the pool over time, there's two natural kind of state representations. The initial state representation, the most obvious one, is let's keep track of the pool reserves. However, it's going to, and we can think of that as, maybe a primal representation in terms of a convex, analysis. Where are we in this vector space? An alternative and maybe a dual representation is let's not define this as a vector, but let's define it through a supporting hyperplane. And that supporting hyperplane is defined through the current spot price. Right. So an alternative representation of what's going on in the pool is instead of me telling you what are the current reserves, I can tell you what's the current implied spot price, and X star and Y star provide a map where I can go from that current implied price to what the current reserves are. It's going to turn out that this alternative representation is much more intuitive and much easier to work with because in financial contexts, we're very naturally concerned with prices. Right. And so this is in some sense the most natural representation to think of as we want to describe the behavior and the mechanics of the pool in a dynamic setting over time. So that's the idea of the pool value function. Let me give a simple example. Again, the constant product case where the product of X and Y are constant, or equivalently their geometric mean is constant. If we plug in that function f into the definition of the pool value problem, and we write out a Lagrangian and do the undergraduate sort of calculus exercise, what we see is that X star and Y star are given as such. X star is L over root P, Y star is L times square root of P, and this is the pool value function is 2L square root of P. Again, these are fairly elementary calculations. All I want to illustrate here is we're not doing anything hard. These calculations end up being, sort of basic, undergraduate calculus. But if you sort of think about it a little bit, there's a bunch of meaning here. Right. So let's first consider the object X star. I'm going to argue that X star of P can be thought of as the LP's passive demand curve for the risky asset, right? What do I mean by passive demand curve? I mean, upfront, when you decide that you're a liquidity provider, that you're participating in the pool, you can anticipate that there's a world of arbitrageurs out there who are going to manipulate the value of the pool and try to make money for themselves. And you can, in advance anticipate through the pool value function what they're going to do. And you can anticipate that as the price goes up, they are going to buy the risky asset from the pool. In other words, the liquidity provider is going to sell the risky asset, and the quantity held in the risky asset is going to go down at a rate of 1 over square root of P in the particular case of a constant product market. So, knowing the presence of arbitrageurs, in some implied way, this object X star is is their implied passive demand curve. Passive in the sense that they're declaring it upfront and they're not modifying it dynamically, and demand curve in the sense that that is how much of the risky asset the liquidity providers will hold as a function of the price. Right. Similarly, we can view the object V of P, the pool value function. We can view that as kind of a payoff function, right? You can because again, if you're a liquidity provider and you decide to participate in this pool, you can anticipate in advance that there are going to be arbitrageurs, and because of that arbitrage activity, in effect, you're implicitly committing that as the price changes, the value of your tokens in the pool will change according to the formula given by the pool value function, right? So again, by virtue of agreeing to participate in this pool, a liquidity provider is implicitly giving us both their demand curve for the risky asset as a function of price, and also implicitly giving us a payoff that they are committing to in terms of the value of assets in the pool. So both of these are going to be suggestive of things like options pricing theory, and so that's why objects like the Black-Scholes model and so on are going to be important, and we'll get to that in Tim's section in the third part of the talk. Now, one thing I want to observe is that in this particular example, the demand curve is downward sloping. It is monotonically decreasing. That's one observation. A second observation, again, in this particular case, the pool value function is given by a square root function, so that is a concave. So that happens to be what happened in this case, but it's actually not a special case. That is universal, and it's important. And it's easy sort of convex optimization lemma to sort of establish that. So we'll establish that in two parts. The first part is that the derivative of the pool value function is precisely the liquidity demand. And that's simply the envelope theorem. Right, so here we have a parameterized optimization problem. The parameter is the arbitrageur's belief of the price P, and we know how to differentiate through optimization problems subject to the right technical conditions. That's simply the envelope theorem, right? So the first part of the lemma tells us that the sensitivity of the payoff to the price is given precisely by the quantity of the risky asset. And in some way, that makes a lot of sense because the quantity of the risky asset is the part of the reserves that's actually exposed to the price. The second part of the lemma really has two parts. The first part is simply that the second derivative of the pool value function is the first derivative of the demand curve, and that's simply differentiating both sides of the first part. But the second part is that this whole that both of these objects are negative, and that's a standard fact also from convex analysis. Here we have a pointwise minimum of linear functions, and that is always concave. So going back to what we had on the prior slide, it's always true that the demand curve is downward sloping. That's what you would expect. After all, it's a demand curve. Similarly, it's always true that the pool value function is concave. And in fact, those are the same fact because the second derivative of the pool value function is the first derivative of the liquidity curve. Moreover, the liquidity curve has some nice properties and interpretations, right? So we can imagine an agent coming in and trading on the pool and moving it from maybe an initial pool price of P0 to a final pool price of P1, and in the process, buying some quantity of risky asset from the pool. And from the pool's perspective, the quantity of the risky asset decreases. And one way to sort of describe this trade moving from this point to this point is simply to use the fundamental theorem of calculus and describe the quantity that's traded as the integral of the derivative of that object. And in particular, the derivative of of this curve, of the liquidity demand curve, we're going to think of that as the marginal utility, right? In other words, when I trade from this price P0 to price P1, and I go through all the prices that are in between, as I go through each price P in between, the amount that I instantaneously trade is given by the derivative of that object. Here, I'm simply taking an absolute value because the derivatives are negative. So in that sense, the derivative of the liquidity demand curve, we're going to call it the marginal liquidity. It's going to be the amount that this structure, this automated market maker, is we're going to trade infinitesimally as we pass through a price level P. And that's going to be a very important object in the third part of the talk when we talk about loss versus rebalancing. So a natural question is, if I were to give you, before we had these demand curves, which would look like 1 over square root of P, if I were to give you an arbitrary demand curve, is that something that can be realized in on automated market maker? And the specific way I'm going to formulate that question is, suppose I have a risky asset demand curve, X star of P, an object like this. Can I pair it with appropriate quantities of the cash asset to hold at different price levels so as to obtain an incentive compatible AMM? What do I mean by that? What I mean by that is, if I give an incoming trader a menu of options defined by X star of P, Y star of P. In other words, rather than telling me what reserves they want to go to, they decide what price level they want to go to. Will it be incentive compatible? Will it be the case that an incoming trader who values the risky asset at price P actually moves me to the state X star P, comma, Y star P, right? So that's the characterization that a risky asset can be realized as a demand curve can be realized as an incentive compatible AMM mechanism. And it turns out that's equivalent to two things. It's equivalent, number one, the demand curve has to be non-increasing. It has to be, downward sloping or monotone and so on. And second, the quantity of the cash asset has to be given by a very specific kind of rule. And this rule is also sort of quite intuitive. This rule states that as I move across prices, the amount of the cash asset that must change corresponds to the quantity of the risky asset that's being traded. Again, that's the marginal liquidity object we talked about on the prior slide, times the price level, right? So again, it says we move from one price to another price. We move along the X asset according to the X star curve, and the Y asset has to be consistent in some way. You have to also be a trading where you trade the marginal liquidity at the corresponding price. So this is the characterization. And in fact, perhaps for those of you from a mechanism design background, this should start to sort of seem a little bit familiar. This is basically a restatement of Meyerson's lemma for single parameter options, right? The way we're sort of viewing this is an incoming agent comes in with a type, the type being P, their valuation of the risky asset. They're presented with a menu of options given by X star of P and corresponding payoffs Y star of P. And as we all know, Meyerson's lemma says that this mechanism will be incentive compatible. In other words, the agent will declare their true value to the mechanism, so long as the allocation rule, in this case the risky asset demand curve, is monotone, and so long as the payment function is given by a particular form, right? So we can imagine not simply, this is kind of now a unifying framework, right? We're going to move away from thinking of automated market makers through the invariant function. Instead, we're going to think about them through this risky asset demand curve. And as long as this risky asset demand curve is downward sloping, is monotone, non-increasing, we know that it can be realized in an automated market maker in a incentive compatible way. So before we had an object which looked like, like L over square root of P. This was the constant product market maker. But we can imagine other things. We can imagine a limit order book, right? So what is a limit order book? That's the, object Jason described at the very beginning. You have orders attached with price levels. And as you cross price levels, those orders trade, right? And so as those orders trade, that corresponds to a jump in a downward jump in the quantity of the risky asset that the pool has. As the price goes higher and higher, orders to sell at higher and higher prices trade, and that generates jumps. So this is completely consistent with our framework. In some sense, we can consider a limit order book as an instantiation of an incentive compatible automated market maker. However, one important difference is it does not satisfy the smoothness conditions that we discussed before. In particular, this object is discontinuous, and so hence the theory that we describe in the third part will not apply, right? So we have constant product market maker. We have a limit order book. We can also think of objects like hybrids. Concentrated liquidity AMM like Uniswap V3 is like a limit order book in the sense that it has this piecewise functional structure. The piece is given by various tick boundaries, however, is different in the sense of rather than jumping at tick boundaries, it has a smooth kind of square root shape inherited by by a constant product structure in between these sort of tick boundaries. So thinking about automated market makers and constant function market makers, not through the invariant function, but rather through the this demand function, is kind of a unifying framework, and in our view is a much more natural way to describe things. And in fact, it's 100% equivalent. If you give me a bonding function, f of xy, I can give you a monotone risky asset demand curve, x star of p, and vice versa. And we've already seen how to do one direction. The first direction, going from the bonding curve to the risky asset demand curve, that's simply solving the optimization problem that defined the pool value function that I showed you a few slides before. So that direction is relatively straightforward. It turns out the second direction is relatively straightforward as well. So it's more non-trivial, however. One thing I should comment is, in general, it's not a injective correspondence, it's surjective. And what I mean by that is for every x star of p, there's many f of xy's that would realize that x star of p. But one kind of construction is to start out with this x star of p, first define the payment rule, if you will, in the Myersonian language, or in the automated market maker language, define how much of the cash asset is held at every price level, and we already know how to do that. And the second bit is to do some convex analysis, which involves, in particular, a perspective transform. Now, I'm not going to go through this, but however, if you're interested in the specific mechanics of why this works out and in what sense it is canonical, I encourage you to attend the paper of Guillermo Angiris, Tarun Chintra, and co-authors on the geometry of constant function market makers, which is part of the regular EC session this year. Right. So where I'm going to end is basically the idea of it's much more natural to think about these automated market makers, not so much through the invariant function, which is usually the way that practitioners, for example, define them. The invariant function, in my mind, is at best a computational device. I think the real way to think about it in terms of what's going on under the hood is through the idea of convex analysis and duality, and that gives us this object of this monotone decreasing liquidity demand curve. In some sense, they're equivalent, but in ways that we're going to see in the third part of the talk, the demand curve viewpoint is much more amenable to dynamic analysis. So I will end here.